All right, so we are at Unit 1, Lesson 1, and we're going to be talking about algebra tiles today. Um, Before we get to talking about anything at a high level of mathematics, anything even that you would consider probably algebra, I want us to go back in time to when you first learned about area, which probably seems kind of like a strange thing to talk about when we're discussing Algebra 2, but I really mean way back at the beginning, back in elementary school, when you were first given maybe a rectangle shape and you were asked to figure out what is the area of this rectangle. And most likely, your teacher gave you a problem that looked a little bit like, let me get this, hold on, there we go, like this. So we have a rectangle. It's broken into a bunch of equal-sized boxes. And you would have been told that these boxes each were worth 1 square unit. Now, the reason that it's worth 1 square unit is because it's a height of 1 and a width of 1, right? Let me see if I can get a little pen here. Write that in, 1 by 1. So this is a square that has an area of 1. It's a 1 unit square. And if you want to know the area of the entire rectangle, you just have to count them up. 1, 2, 3, 4, 5, and you would continue on. 6, 7, 8, 9, 10, 11, 12, 13, 14, and the last one would be 15. And so you would know that the area of this rectangle is 15 units squared. And I'll write that down actually before I say something else. 15 units squared.
But it probably didn't take too long you either figured out or your teacher informed you that there's a pattern here, that each row
is made up of the same number of squares. So like row number 1 has 5 squares, row number 2 has 5 squares, row number 3 has 5 squares. And we can turn that into a multiplication problem, also known as the area formula, because the area formula says that if you take the length or the height of a rectangle and you multiply it by its width, then you will end up with its area, which in this case was 3 rows of 5 square blocks, which gives us, of course, 15 units squared. So 3 by 5, we multiply and we get the same answer. So not the most difficult math problem you've been asked to do probably in a while, but something that we can all agree upon, something that was probably foundational for you in understanding what geometry and area was all about. So I want you to take that thinking and apply it with me to this picture. It's also a rectangle. It does have some yellow unit squares down here at the bottom. We'll assume that these are all 1. Just like they were in the last one. See, over here we had little 1 unit squares that were yellow, same 1 unit squares here. But now we have some larger unknowns here. For instance, these green blocks. How big are they? It's hard to count them up and talk about area if we don't even know how big they are. And then we have this very large square over here. We really don't know how big that one is. So how are we going to figure out what the area is if we don't even know the size of the blocks? Well, this is where higher level algebra comes in. It's where we use x. Anytime that we're talking in algebra and we don't know what something is, we give it a variable name. And so the most common, of course, is x. So let's do that in this picture here. Looking at, let's look at the green ones first. This green block has one dimension that we know and one dimension that we don't. What I mean by that is this. There's a width here at the bottom that matches our 1 unit block. So that means it has to have a width of 1. They wouldn't be able to match up so nicely if that wasn't true. But it also has a height that we don't know. That's unknown, a height or a length. And so we will call it x. I hope my scribbling doesn't bother you. It's a little chaotic there right now. But just think about it this way. It's x is the height. The width is 1. Well, if I have a rectangle with a height of x and a width of 1, I can figure out what it is by taking the width times the height and multiplying it. 1 times x. Well, that means that it has an area of x, 1x. And that's what the green blocks are. In fact, I have one right here that you can look at. It's green just like in the picture. And here's our little 1 block, and it does match up very nicely right here on the bottom. Of course, it doesn't here. And if we try to match them up, there's always a little bit left over. It's an unknown. We can't know for sure how long this is, and that's intentional that it's been made that way. It's 1 by an unknown, by x. Therefore, this is an x block. This is a 1 block. 1 by 1, 1 by x. Let's go find out what the blue one is. So this means, I'm going to erase. I'm just going to clear these out. Let's rewrite it this way. So we know this is a 1, this is a 1, this is a 1. These are all 1s. Now we know that the greens are all x's. So how big is the blue square? Well, we can use the same trick that we used in the our last little mystery, and that is we can figure out the dimensions of the blue square by comparing it to what it's next to. The two long sides of the blue square match up to the long sides of the x rectangles, which means that this is really an x by x square. It has an x dimension by an x dimension. So the question is, what is the area of the square itself? Well, if I have a square with a length of x, again, how do I know that? Because it matches the x, and it has a width of x. X times x, we know in algebra, in basic algebra, if I take a variable times itself, it becomes that variable squared. So this is an x squared, which should make sense. It is a square and it has a dimension of x, so it's an x squared block. So instead of this little question mark, we will replace that with x squared. Okay, so now let's go back to our original basic geometry problem where we were trying to find area. We found the area of this rectangle by counting up the pieces, right? 1, 2, 3, 4, 5, all the way up to 15 squares. Can I apply that here? Well, yes, I think we can. We're just going to have to do it in pieces because we have 1, 2, 3, 4, 5, 6 ones. But we also have 1, 2, 3, 4, 5 x's, and we have 1 x squared block. Well, I'm going to have to add those together. Can I combine like terms here? No, not really. I can't call an x squared an x block. I can't combine them at all. So I'm going to write this as x squared plus 5x plus 6, and I'm going to say that, my friends, is the area of this rectangle. How did I do it again? I just counted up the pieces. We defined the pieces and then we counted them up. Now, we could have called those unknowns m instead of x, and then it would have been m squared plus 5m plus 6. We could have called it z, but no matter what letter we call it, each of those pieces would still be defined as the variable squared. Well, I should say the whole piece would be the variable squared plus 5 of the unknown variables plus 6 of the ones. It will always have that pattern because it's defined innately in its shape, not by some abstract somebody coming up with random algebra pieces. Okay, so going back. Remember, for each algebra or for each geometry area problem that we can count the pieces up for, there is a shortcut. And that shortcut says that we don't actually have to count up the pieces. We could just multiply the length times the width, or the width times the height, or the length times the height, however you want to say that. The two dimensions, and they can be multiplied. So let's see, can we apply that to this new problem? Well, I can decide on a height and a width, and it really doesn't matter if I decide to make the left side the height or the right side the height, or if I decide to make the bottom the width or measure along the top. It's the same size. But can I define what those are? Well, the good news is none of our unknown variables have changed since we calculated the first time. So if I want to measure the height over on the left here, I need to go back to how we define these things to begin with. And we know that the blue square has a length of x. How do we know? Because that's how it was defined. It's an unknown dimension by an unknown dimension. So this is x. We also know that the green blocks are 1 by x. That's the dimension of them, 1 by x, because they match up with these cool little 1 unit blocks. So this is the height of 1. And the same thing here, right? It's a height of 1. It's the same as the height of one of these yellow blocks. So the height of our whole rectangle here is x plus 2 ones. So it is x plus 2. We can also define the width, and like I said, you can do it along the top or the bottom, it doesn't matter. We're just measuring. So this is an x, this is a 1, another 1, and a third 1. So the dimension along the bottom is an x plus 3 ones. So it's x plus 3. So what I found, and I'm just going to, actually I'll draw it up here so I can talk at you and point at the same time. So this is my interpretation here of our squares. All right, so we have the x, this is x plus 2 is the dimension on the left, and we decided that x plus 3 was the dimension along the bottom. And originally when we added up all the pieces, we decided that the area was 1 x squared block, 5 x blocks, and 6 ones. How does that compare to the fact that we should also be able to label this rectangle by length times height? Well, the length, of course, let me use a slightly darker one here. So the length is x plus 2, and the width is x plus 3. And from last year or the year before, whenever you were in Algebra 1, you would have learned that I can take two factors like this and I can simplify it, right? So I've just listed, this is the length, this is the width. Let's find out what happens when I multiply it out. We share, pink, we share that x to, we are going to double distribute, so we distribute the x first, so that would be x squared plus 3x. Then we distribute the 2 times x, 2 times 3 is 6. And when I put the like terms together, the 3x and the 2x here, I end up with this very interesting and familiar expression, x squared, plus, let's see, 3x and 2x is 5x, and 6 ones. And lo and behold, I've gotten the same answer. And so what we've shown is that there are two ways to label the area of a rectangle, right? It's the same thing that we did over here. Oh, wait, hold on. Let me bring it up. There it is. Same thing we did over here. We counted up the pieces the first time, and then we multiplied the dimensions, and we showed you can find the area both ways. It shows that they're equal. Length times width is equal to adding up the squares. Well, we've also now shown that we can do the same thing with our more complicated rectangle. You can add up the pieces even when you don't know what the dimensions are with these unknown x's, and you can either multiply the length times the width, or you can just count up the pieces and it's the same thing. There's a lot more that we can do with this. I feel like I need to hide away from all my numbers here. Here, I'll erase them. You can pause and rewind if you didn't get all that down. What we've learned is that there are two ways to describe rectangles in algebra with algebra tiles that we will be using in the same way that we've done with geometry in the past. Now there's some other significant pieces, like we'll talk a little bit more when we're together about what happens if you have negative dimensions. Well, we never talk about negative dimensions in geometry because space, physical space, is always positive, right? It's kind of like when you measure distance, you always measure a positive distance. But in mathematics, or actually even if we start talking about physics or some more complex concepts, we have to include the idea that something could have a positive value or have a negative value. And these algebra tiles are going to give us some consistency in that area too. I'm just not going to put it in the video for now. We'll do that more in a hands-on sense. But we're going to be able to use these not just to show like, hey, here's a rectangle and let's go ahead and show the two ways we can find its area. We're actually going to be able to use these to factor complicated equations. So for instance, let's say I knew that, actually let's come over here. Let's say that I knew that I had the equation x squared plus 3x plus 2. And I was asked, how do I put this into factored form? How do I give an equivalent expression for x squared plus 3x plus 2 in its factored form? And we're going to use algebra tiles to decide what those dimensions need to be. And I think after you play around with them a few times in class, actually we'll do it for more than just a few times, you're going to be able to start internalizing this idea in a much more intuitive way, not just as a bunch of rules that you have to memorize. We will work through the rules and talk about what would be helpful to memorize in the long term, but hopefully it will stick a little better after we work through it. So no homework besides just writing down some of these example problems. It is important to define, remember this is an x squared, actually I'll give you the positive sign, an x squared, this is an x, and this is a 1. And then maybe you want to write down a little bit about those example problems that we did as well if you haven't already. And that's it. I will see you in class.